How do scientists recreate the power of the sun on Earth? It all starts with nuclear fusion. Nuclear fusion happens when two very light atomic nuclei combine and smash together, releasing a huge amount of energy. But fusion can happen in solid, liquid, or gases. So, what state of matter do we need? Plasma. Plasma is an extremely hot state where electrons break free, creating charged particles. At temperature above 100 million degrees Celsius, these particles move fast enough to overcome their natural repulsion and fuse. The main fusion reaction uses deuterium and tritium. They fuse to form helium, release a neutron, and produce large amount of energy. To create this fusion condition on Earth, scientists use a specialized machine called a tokamak. China's East tokamak, often called the artificial sun, is one of the world's most advanced fusion research devices. The word tokamak stands for toroidal chamber magnetic coils. It is a donut-shaped vessel surrounded by powerful magnetic coils. These magnetic fields confine the plasma, keeping it suspended and preventing it from touching the reactor walls. Inside the East, the plasma is kept hot, dense, and stable for hundreds of seconds, allowing fusion reactions to occur. When deuterium and tritium fuse inside the tokamak, enormous amounts of clean energy are released, demonstrating the potential of fusion power.
Today, I would like to explain the difference between conventional nuclear energy and the artificial sun, also known as nuclear fusion. First, conventional nuclear energy uses nuclear fission, which means splitting heavy atoms like uranium to produce heat and electricity. This type of energy is already used worldwide for power generation. However, it produces radioactive waste, which is dangerous and it carries risks of major accidents such as Chernobyl and Fukushima. On the other hand, the artificial sun, developed mainly in China, uses nuclear fusion. Fusion combines light atoms like deuterium to form a heavy atom, similar to how the sun produces energy. Currently, this technology is mainly for scientific research and it is not used for commercial power generation. In the future, fusion energy promises a cleaner and safer energy source as it produces less dangerous waste and has no risk of large explosion.
Fusion energy is often described as the holy grail of clean power, and here's why. First, fusion produces no carbon emissions. Unlike coal or gas, it doesn't release greenhouse gases, so it could directly help slow climate change by cutting the main driver of global warming. Second, fusion has an abundant fuel supply. It uses hydrogen, isotopes found in seawater, and lithium, resources that are virtually unlimited. In fact, the deuterium in our oceans could power humanity for millions of years, making fusion truly renewable. Third, fusion generates minimal waste, unlike nuclear fission, which leaves behind long-lived radioactive materials, which main byproduct is helium, a harmless gas. This makes it cleaner, safer, and easier to manage. Put together, fusion offers a future of energy that is safe, sustainable, and climate-friendly. If we can make it commercially viable, it could transform the way the world is powered.
How can nuclear fission help to reduce the climate change if it works in the future? Global warming is caused mainly by greenhouse gases such as carbon dioxide released from burning fossil fuels. These gases trap heat in the atmosphere, causing Earth's temperature to rise. Nuclear fusion produces energy without releasing carbon dioxide or other greenhouse gases. According to the International Atomic Energy Agency, fusion does not contribute to global warming because it does not emit greenhouse gases during the operation. By replacing fossil fuel power with plant fusion energy, the amount of heat trapped in the atmosphere can be reduced. Next, air pollution and climate change are closely connected. Burning coal and oil releases gases and particles that not only damage human health, but also traps heat in the atmosphere. Nuclear fusion does not involve combustion, so it produces no smoke, no soot, no toxic gases. The Clean Air Task report states that the nuclear fusion energy has zero carbon emission and a very low environmental impact. Cleaner air also helps reduce warming caused by the pollution and improve overall climate condition. Moreover, one of the most visible effects of climate change is the melting of glaciers and polar ice caps. This happens because of rising global temperatures in the air and ocean. Scientific studies shows that reducing carbon emission is essential to slowing down the ice melting process. Lastly, climate change increases extreme weather events such as flood, droughts, heat waves, and stronger storms. These events are driven by excess heat trapped in the Earth's atmosphere. By cutting greenhouse gases, nuclear fusion helps to reduce the root cause of climate instability. The MIT Energy Initiative confirms that the fusion will play a major role in the future by lowering the carbon energy system, helping to stabilize the climate change over time.
Alright, as we know, we are using the concept of nuclear fusion in this project. And in nuclear fusion, we need to combine the core of two atoms together, which are deuterium and tritium. As we know, the core of two atoms contain protons, which are positive charge. And when these two positive charge, we try to combine them, of course, they are nuclear repulsion because they don't want to be combined. But in order to make this happen, we need to apply very, very high pressure. And of course, if we want to apply very high pressure, we need a very, very high temperature. And the temperature is 100 million degrees Celsius. One more thing is, if we want to make something as our energy resources, of course, it needs to survive for a very long time. However, in 2025, the experimental advanced superconducting tokamak by Institute of Plasma Physics in China, they only can maintain the nuclear fission for around 1066 seconds, which is 70 minutes. And now the question is, are we actually get more energy than what we actually provide in these experiments? And now, in fact, we are still having deficit in any nuclear fission experiment until today. For context, Q value or EROI is actually the ratio between the energy that we provide into the reaction over the energy that we get back from the reaction or from the energy resources. And based on the latest 1997 nuclear fusion device, JET tokamak by ITER, it only can provide 16 megawatt after they provide 24 megawatt. That means the Q value is around 0.67, which means deficit energy.